Okay, so for the first video, we will now be solving the first example from your module entitled E428-1. So this module is actually discussing your Boolean algebra, and I hope you've read it already. So it's basically giving you the definition and importance of Boolean algebra. So similar to how you do your algebra back when you were in first year, your algebra is actually used to relate equations, right? So if you have one equation, that doesn't mean that you cannot change the form of that equation, because apparently you have other forms of that equation which means the same. And that can be useful when it comes now to your digital circuits, because a function which might contain several literals, when we say literals, those are simply your prime and unprimed variables. So if you're going to count the number of literals, say, and um, it's turning out to be a lot, like say you have 10, 11, 12 literals, that doesn't mean you can simplify the function. You are able to simplify that given Boolean function if you know how to apply your postulates and theorems. You can reduce your number of literals, and correspondingly, if you are reducing your number of literals, you are also reducing now your number of operations. So thereby reducing the length of the function in totality. And if you do that, that's going to that's gonna go a long way, because it's going to translate as a much simpler circuit when implemented. So a very long Boolean function would of course mean you have a very complex digital circuit, whereas a very short Boolean function actually means you have a simpler digital circuit. So how do you do that? Again, you make use of your postulates and theorems. Your postulates actually came from the Huntington postulates, which is not unique to Boolean algebra. Your Huntington postulate is used in other forms of algebra, but it's also applicable to Boolean algebra as discussed in your module. However, the theorems that were presented can actually be derived using your Huntington postulates. So, all in all, you have six Huntington postulates, if I can remember it right, and six theorems. So, six postulates, six theorems. We attempt to simplify the following functions. So, we start with number one, and the function is x or x prime y. There. So what we have to do again is to reduce this to a minimum number of literals. Currently we have 3. So who knows, if we apply the theorems and postulate, we might be able to reduce this to 2 or even 1 if it's possible. So what's the first step here? So I am actually looking at a postulate that implements your distributive law. So what postulate is that? That is postulate number 4. So recalling your postulate 4, you can do you can do your distributive property if the function looks like, so let's recall postulate 4. If a function looks like x and y or z, I'm omitting already the dot operation here, but I hope you know that that still means and. If there's nothing in between the groups, it means and. So this can be distributed. The x variable here can be distributed. So this becomes x and y, or x and z. There is really nothing new here because you've been doing your distributive operation already from your algebra. So it's similar. However, one thing that is new is you could also perform your distributive over the OR operation. So postulate 4 also allows you to do something like an x or y and x or z. So the x is distributed. You cannot do this from your basic algebra, but you can do this in Boolean algebra. This means that if you do the truth table for this, it's similar to this one. So, which is exactly what I am looking at for the first example. So, it's of the same form. So, I want to do distributive operation. So, if I distribute the x over the OR operation here to the x prime y, then this should now become x or x prime and x or y. And again, that is from postulate number 4. There. Next. What about the next one? So if you look at this current function, x or x prime and x or y, I hope that reminds you of another postulate when you look at the first group. So the first group here, you have an x or x prime. So if you go back to your notes, you actually have there your postulate 5. And your postulate 5 suggests that if you take the OR of a variable to its complement, then you should be able to obtain 1. Will that make sense? Well, basically, yes, because you only have two values, two possible values in Boolean algebra. It's either just 0 or 1, and the complement of 0 is 1, and vice versa. Hence, if this is 0, then this must be 1. 0 or 1 should give you 1. On the other hand, if this is 1, then this must be 0. So 1 or 0 is still 1. So this is valid. X or x prime is 1. However, it's the other way around if you take the and of a variable to its complement. Because it's now an and operation, and this two successive variables, one x and the other one x prime, suggests that one is therefore equal to 1 and the other one is equal to 0. So either this one is 1 and this one is 0, or this is 0 and this one is 1. Either way, you have 1 and 0 or 0 and 1, which should always give you 0. So that is your postulate 5. So it's a postulate concerned with your complements. So I'm looking at the first group here, which is x or x prime. So if we apply your postulate 5, you know that x or x prime is actually 1. So 1 and x or y. So this should now be from postulate 5. And I think we can still simplify this. Now that we have a 1 here, I want us to recall this time your identity elements from postulate 2. So postulate 2 suggests that we have an identity element of 0 for the OR operation. So if you take a variable or 0, the result will still be that variable. And we can check that, of course, because if this is 1, 1 or 0 is 1. If this is 0, 0 or 0 is 0. So 0 is the identity element for the OR operation. It means that if you take a variable, take the OR of a variable to 0, the result will be that same variable. The identity element for an AND operation, meanwhile, must be 1. And again, we can double check that 1 and 1 is 1, 0 and 1 is 0. So, similar to this, from our example, x here is the x or y, okay? And this group and to 1, so that can be simplified for this as x, for this one as x or y. Coming from postulate 2. So I guess there's nothing more to simplify. This is the final answer.